Hello, this is Dr. VC Sontake and I am going to teach the course Heat Transfer. Objectives of this video lecture are: we will be discussing need and importance of extended surfaces and to define and classify fins. So let us start our discussion with heat transfer through extended surfaces. Now here one term comes into picture: extended surfaces. Let us try to define this term first. So let us discuss what is extended surfaces and what are their need and importance of them. In order to understand the importance of extended surfaces, let us first discuss heat transfer enhancement in convection and the factors upon which the heat transfer rate enhancement in convection depends. We know convection is the process. Convection is the mode of heat transfer by which heat transfer takes place between solid surface and fluids and between two layers of fluid. We also know convections are of two types: free convection and forced convection. In free convection, as you can see here, heat transfer takes place between solid surface and fluid by virtue of temperature difference only. The driving potential in case of free convection is temperature difference only. The temperature difference causes variation in density, and that variation in density gives rise to buoyancy forces, and that buoyancy forces causes movement of the fluid, because of which heat transfer takes place. So as you can see here, there is a solid surface at temperature Ts and it is exposed to the air, let's say at temperature T infinity. So heat transfer will take place by virtue of temperature difference only. Another type of convection is forced convection. Here, in addition with temperature difference, a mechanical agency is employed to enhance the heat transfer rate. This mechanical agency, such as fan, blower, compressor, turbine, is employed to force the fluid to flow over this surface. So this is called as forced convection. Now, as far as rate of heat transfer is concerned, heat transfer rate in forced convection is much higher than in case of natural convection. Now, why it happens, that we will be discussing in due course of time. So here my purpose is to enhance heat transfer rate in convection. So we have one method, forced convection. But what happens in many real life situations, we cannot use the forced convection setup. That is, we cannot use a mechanical agency to enhance heat transfer rate. That means we need to restrict to free convection or natural convection condition only. And if we want enhanced heat transfer rate in case of free convection, we don't have lot of options actually. So still, let's say we have free convection or natural convection conditions where heat transfer is taking place by free or natural convection, and we want to enhance heat transfer rate. without the fan. So first let us discuss on what factors the heat transfer rate in case of convection depends. So we know Newton's law of cooling gives us heat transfer rate in convection, and it is given as Q is equal to H into A into delta, where H is called as convective heat transfer coefficient or film coefficient or heat transfer coefficient in convection. Its unit is watt per meter square Kelvin. A is surface area available for heat transfer. Now surface area is very important parameter in case of convection heat transfer, and how it is decided we have discussed in unit number 1 in great detail. And finally delta T is the temperature difference between surface and cold fluid. Now let us discuss one by one the effect of each parameters on the rate of heat transfer. So let us first discuss the effect of convective heat transfer coefficient keeping surface area and temperature difference between two entity constant. Now from from Newton's law of cooling, we know that heat transfer rate in convection is directly proportional to H, that is convective heat transfer coefficient. And this convective heat transfer coefficient depends upon fluids and other thermal conditions. Let us consider a body at temperature Ts is exposed to the air first at temperature T infinity, such that Ts is greater than T infinity. Depending upon the temperature difference and prevailing thermal conditions, let's say convective heat transfer coefficient is H suffix air, for this case 1. Now let us consider the same plate at the same temperature Ts is exposed to the water now. Here also Ts greater than T infinity. And temperature difference in both these cases are same. Let's say convective heat transfer coefficient for water is H suffix water. So here what we are going to do, the surface area of the plate is same, temperature is same, that is temperature difference is also same, but we have exposed this plate to different types of fluid. In case 1 it is air and in case 2 it is water. Now what happens? The convective heat transfer coefficient for water is much greater than convective heat transfer coefficient for air. So as a result of this, heat transfer rate from the plate exposed to water is much greater than heat transfer rate to air. That is, if we want to enhance the heat transfer rate in free convection, we can expose the surface to the fluid with higher convective heat transfer coefficient. Then effect of surface area keeping H and delta T constant. From Newton's law of cooling, the rate in convection Q is directly proportional to the surface area. That means more is the area, more will be the heat transfer rate. So let us consider a plate having surface area A1 is exposed to the air for the sake of convenience as a fluid, and convective heat transfer coefficient is H. Let temperature difference is Ts minus T infinity. Now the same plate is at same temperature Ts and surrounding fluid temperature T infinity, that is air, is exposed, but in this case its surface area has been increased. So here we are keeping H value as constant because the plate is exposed to the same fluid. Here we are also keeping delta T as constant because in both the cases surface temperature is same, fluid temperature is same. So what happens? Surface area in second case is more than the surface area in first case. So heat transfer rate in convection will be larger in second case as compared to first case. So if we want to increase the heat transfer rate in free convection, we have to increase the surface area of the body from which heat transfer rate is to be increased. Then effect of delta T, that is temperature difference, keeping H and A constant. Once again from Newton's law of cooling, heat transfer rate in convection, Q is directly proportional to delta T, where delta T is Ts minus T infinity. If surface is heated, fluid is cold. It can be vice versa as well. So let us consider once again a plate of area A and surface temperature Ts1 exposed to the air at temperature T infinity. Now the same plate with the same surface area is exposed to the air once again at temperature T infinity, but this time its surface temperature is Ts2 such that Ts2 is greater than Ts1. Now normally surrounding fluid temperature is remaining constant because it is a reservoir temperature. So temperature difference, since Ts2 is greater than Ts1, so Ts2 minus T infinity will be greater than Ts1 minus T infinity. So since Q is directly proportional to temperature difference, heat transfer rate in second case will be higher than heat transfer rate in first case. So from this analysis, what can I conclude? If we want to enhance heat transfer rate in free convection particularly, we can do so by either increasing H value or A value and delta T value. But again, the job is not so easy because nature tests the ingenuity of an engineer. Now again, it is a free convection condition and we want to enhance the heat transfer rate, but we can't enhance H, A and delta T. So we have to keep H, A and delta T constant. Many times the area A is the geometrical surface area of the hot body. What does it mean? That means in order to increase the heat transfer rate, if I increase the surface area, obviously its geometrical surface area will be increasing. But the functionality aspect of that part does not allow to increase its surface area more than the geometrical area. So what is the solution then? How can I enhance the heat transfer rate in free convection if we have all these three constraints? Can't change H, A or delta T. So this is the problem. Now solution to this problem is we can increase the heat transfer rate from the base surface. Let us say this is the base surface at temperature Ts. It is exposed to the environment T infinity, and I want to increase the heat transfer rate from this base surface to this fluid, let's say air, and its geometrical area is surface area is A. So in order to enhance the heat transfer rate from this base surface exposed to the air at temperature T infinity without changing the value of H, without changing the value of Ts or T infinity, in turn Ts minus T infinity, I can enhance the heat transfer rate by attaching some surfaces more than one. So these attached surfaces which are used to enhance heat transfer rate from the base surface are called as extended surfaces in general. So these are called as extended surfaces. The extra surfaces which are attached to the base surfaces in the form of protrusion are called as extended surfaces. So what they do actually, these extended surfaces enhances the surface area required to enhance heat transfer rate without changing the original or geometrical surface area of the base surface. Okay, so here what will we do? What these extended surfaces will be doing? They will be increasing the area available for heat transfer. So if I want to calculate now heat transfer area, it will be summation of geometrical area of the base surface to, let's say these extended surfaces are in the form of cylinder and they are of 6 number, so 6 into pi dl. So this will be the total surface area available for heat transfer. So heat transfer rate with base surface area, let's say it is Q1, and heat transfer rate with extended surfaces is, let's say, Q2, and in second case heat transfer area has been increased tremendously, so heat transfer rate in second case will also get enhanced. So that is the purpose of extended surfaces. Now these extended surfaces are also called as fins. The word fin is derived from the fins of the fish. The fins of the fish are used to help him to swim, whereas fins attached to the base surface are used to enhance the heat transfer. And these fins attached to the base surfaces are so effective, they can enhance the heat transfer rate something in the range of 200% to 400%. So that is something very a unique feature of extended surfaces. So these are few more illustrations of heat transfer from extended surfaces. In case 1, heat transfer rate from base surface is HA delta T. However, in case 2, the heat transfer rate from the total system will be heat transfer rate from base surface plus heat transfer rate from finned surface. Let's say this is Q2, this is Q1. So because of the provision of fins, heat transfer rate in second case will get increased. Some engineering systems with fins. So in daily life, we can come across so many engineering systems, not only from mechanical engineering, from different branches of engineering. For example, as you can see here, there is an electric machine like motors and transformers. They are also provided with fins. These are nothing but fins to enhance the heat transfer rate. Now from where the heat is generating into these electrical machines, so we know all these two different machines are carrying current, let's say of magnitude I, and their electrical resistance is Re. So from Joule's effect, this much heat will be generated while electricity is being flown into these two electrical machines. Now this heat generated is actually unwanted, undesired, and if it is not dissipated to the environment, it will unnecessarily enhance the surface temperature of either this electrical motor or transformer, and this increased temperature will disrupt the functionality of electric motor or transformer. So by providing the fins, we can enhance the heat transfer rate, and these two electrical machines temperature will be remaining within optimum limit. And we can also see the heat transfer rate from transformer surface to the air is by free convection. No mechanical agency is employed. So here fins are the only options to enhance heat transfer rate and to keep their temperature within safe limit, optimum limit. Similarly, these are two mechanical systems, the IC engine, these are the fins, and in refrigerator, on the back side of your refrigerator, there are condenser tubes. These are basically condenser tubes, and heat transfer rate takes place between the refrigerant flowing inside the tubes and surrounding air. So in order to enhance the heat transfer rate, these are the fins provided. So these fins actually enhance the heat transfer rate area and hence heat transfer rate. So you can come across so many such systems in the real life where fins are provided to enhance heat transfer rate in free convection conditions. So try to sum up, try to look into some more engineering systems. Now classification of fins. So fins are classified as uniform cross-sectional area fin and variable cross-sectional area fin. In this diagram, different types of fins are attached. These fins are demonstrated. The first fin is straight fin of uniform cross-sectional area. This is the base surface. So this is the base surface to which this rectangular shape fin is attached, and its area is constant from the base of the fin till its tip. Actually, this is called as root of the fin and this is called as tip of the fin. So if cross-sectional area of the fin does not get changed from root to its tip, it is called as uniform cross section area fin. In second case, it is a straight fin of non-uniform cross section. This is its root where its area is maximum, and this is the tip of the fin where its area is minimum, and it is continuously decreasing, so it is a fin of non-uniform cross sectional area. Then in third case, fins in the form of circular discs are provided over cylindrical surface. So this is called as annular fin. In fourth case, there is a truncated cone attached to the base surface, and it is also called as spin fin. So from here we can observe what do you mean by fins of uniform cross sectional area and fins of non-uniform cross sectional area. Then there are different types of fins: straight rectangular fin, splined fins. When rectangular fins are provided over the shaft, cylindrical shaft, they are called as splined fins. Actually, these are the splined fins. Then in non-uniform fins. So in case C, the area of the fin is varying from one side, while its top side area is remaining constant. This is also a non-uniform cross-sectional area fin. In second case, area of the fin is varying from both the side, that is top and bottom, from root towards the tip. These are annular fins. Fins in the form of circular discs are provided over the cylindrical surface are called as annular fins. These are cylindrical fins. The shape of the fin is cylindrical, attached to the base surface. So cylindrical fin is also called as spin fin. In this case, a truncated cone is attached to the base surface. It is also called as spine. Spine fin are also of the shape like this. When a cone is attached to the base surface, it is also called as spine. And in the last case, a parabolic shaped fin is attached to the base surface. So this way there are different types of fins we can attach to the base surface to enhance heat transfer rate. Obviously the selection will be governed by so many parameters. So learning outcomes of this video lecture are: after watching this video, one will be able to discuss need and importance of extended surface, and also will be able to define what is extended surfaces. You will also be able to define and classify different types of fins. So with this, I come to an end of this video lecture. Thank you for passionate listening. Happy learning.